Okay, so far in this simulation systems course, we have seen that the dynamics or the dynamic system behavior is described by linear differential equations. And since we are concerned with linear time invariant system, such differential equations turns out to be equations with constant coefficients, right? And in last class, we discussed about the solution of linear differential equations, ordinary linear differential equations with constant coefficients, employing the principle of Laplace transform. And while discussing that, we saw that for different types of inputs, given a differential equation which describes the behavior of a dynamic system, for different types of input, we need to solve the same differential equation repeatedly to obtain the corresponding output. So for some second, third, or fourth order system that may be possible, but for systems with order more than 4 or even sometimes more than 3 even, the situation becomes very cumbersome. The solution of differential equation, finding solution of differential equation is not that straightforward. For that, what we need is a general mathematical expression that should relate the output to the input of a system. And that particular relation is sometimes referred as transfer function. Okay? Now, I guess you have a brief introduction to the transfer function, or you know the definition of a transfer function. Yes, anybody? How do you define the transfer function of a system?
Output response,
But
Laplace transform of
response by
output
excitation.
response.
Anyone of you? Yes. Follow?
The response to the excitation.
No, not complete. Anyone else?
Sir, ratio of the Laplace transform of the response to the Laplace transform of the excitation with all the initial conditions set to 0.
Right, that is fine. That is the definition of transfer function. Okay, that is, it is defined as the ratio of the Laplace transform of the output or the response to the Laplace transform of the input with all the initial conditions set to 0. Now, what is the basic function of the transfer function? We should discuss about that, and we shall consider some of the typical problems of determining transfer function of a given system. Now, to start with, we all know that the input-output relation of an LTI system with continuous input is described by differential equation. Let a linear time invariant system be defined by the following differential equation. Say, this is a differential equation depicting the input-output behavior of a LTI system. Continue until we get n minus 1 plus yt, and that is equal to, say, b0 and so on. Ultimately, we reach bm minus 1 dxt dt plus bm xt. Now, obviously, we'll assume in this case, first assumption is n is greater than equal to f, and these two functions x and y, where yt is your output, or this is called the response function, and your xt is your input. This is for the driving function. Now, the theory is that if, and obviously this AI, all this AI and BI, they are real constants. Now, it can be stated that once the input xt is known for t greater than equal to t0, along with the initial conditions of yt and its derivatives. Okay, so for t greater than t0, if you know xt and the initial conditions for yt and the derivatives, okay, and this initial condition of derive are specified at t equal to t0. So if this the information is available with you, information are available with you, then you can find out yt for all t greater than equal to t0 by solving this differential equation. So given xt, a known input for t greater than t0, the initial time, and you know the initial conditions of yt and all its derivatives at t equal to t0, then you can derive the expression for yt for all t greater than t0 by solving this differential equation. Okay, so what we do, suppose the system order is defined by n. If the system order is relatively low, say 2 or 3, it can be possible to solve this differential equation. But for higher order systems, it becomes very cumbersome to solve for this differential equation for different sets of input. So for that, what we will do, we'll convert this differential equation into Laplace domain, and we'll obtain the Laplace transform of output and input, and from that ratio, we'll get the transfer function. With only restriction that we'll assume that the initial condition of yt and all its derivatives are zero, and that is called that the system is a initially relaxed system. That is, not only yt is equal to zero at say yt is equal to zero, but all the derivatives of yt at t equal to t0 are also zero. Okay, because only yt is equal to zero will not mean the system is a relaxed system. Suppose yt0 equal to 0, but y dot t0 or y dot at t equal to t0 is not equal to 0. Then what will happen? It will have some value at t equal to t0 plus, because the rate of change of yt is there. So to ensure the system is absolutely relaxed, we have to ensure that not only yt0 is 0, but all of the derivatives at that time, the initial time is also 0. Okay, so they are all zeros. Then only you can say it's a relaxed system, and you can proceed with determining the transfer function. So if we proceed with the determination of the transfer function, what is the transfer function? I'll just remove this portion because I need to write the transfer function. But this transfer function will actually eliminate the burden of solving this differential equation repeatedly. So the transfer function, say GS, it will be defined as Laplace transform of output divided by Laplace transform of input with initial conditions equal to 0. So if you apply this, what will be the GS here? Yes. The GS will be the numerator polynomial, and the denominator polynomial will be obviously assume n to be greater than equal to f. So this will be the transfer function corresponding to this differential equation or the transfer function of this particular system. Now we need to clarify a few aspects of the transfer function. What are these aspects? This applicability of transfer function or the concept of the transfer function is only limited. Now one point, let me just point it out. Comments on transfer function. What are the comments on transfer function? The applicability of the concept of transfer function is only limited to linear time invariant system. That is, for nonlinear system or for time varying system, this concept of transfer function will not be valid. Again, if you have a SISO system, then you can uniquely determine the transfer function GS. SISO means single input, single output system. But if you have multiple input or multiple output, then instead of GS, say for multiple input, multiple output system, what you'll get is a transfer function matrix. Things like this. Because there are multiple inputs and each of the transfer function will relate each of the output to a corresponding input. So it will be transfer function matrix. So the basic feature of the transfer function will only be applicable or more suitable for such SISO systems. It is single input, single output, linear time invariant system. For time varying system or for nonlinear system, this concept doesn't hold, right? So the transfer function is obviously defined between a pair of input and output in Laplace domain. Okay, that is, it is defined as a ratio of output to the input in Laplace domain with all initial condition set to 0. Now the next question that arises, if you have some non-zero finite initial condition, then what to do? Then the concept of transfer function will not be valid. Then what we have to do for non-zero initial condition, we have to take help of another modeling technique that is called state space model. Once I am done with this transfer function modeling, I shall also include the concept of state space model, maybe in the next class. Okay, this is capable of taking care of non-zero initial condition, because having zero initial condition is a very, very idealistic situation. In most of the situations, we have some non-zero or finite initial condition. Then the transfer function of a system is basically a mathematical model. It's a mathematical model of the system, and it is an operational method of expressing the differential equation. Okay, that relates the output to the input. So it's basically a mathematical model, and that expresses the operational characteristics of the differential equation that relates the output to the input. Okay? So it's basically a mathematical model. Sixth point is very important. Is an inherent property of the system. Okay, and therefore it is an inherent property of the system, and therefore I think I should work on my handwriting. It's very of the system. That means the transfer function will be independent of nature and magnitude of input. This is very important. So whatever input you provide or excitation you provide to the system, it will not affect the transfer function because it is an inherent property of the system, and it will be independent of the nature or magnitude of the input. Only provided the fact that it's an idealistic situation. If you provide very high input, one situation may occur where the output of a system is so high that it reaches the level of saturation. Then it may behave in a nonlinear fashion. So as soon as you start behaving in a nonlinear fashion, the concept of transfer function will not hold. So as long as the system is in the linear range, the transfer function concept is valid, and the transfer function will be independent of the nature of the input or the magnitude of the input. That is, if you know the Laplace transform of the input signal, say Rs, then the corresponding output Ys will be simply given by Gs into Rs. And this Gs will be the inherent property of the system, and it will be completely independent of the type or magnitude of Rs, as long as the system lies in the linear region of operation. Okay. Now, following this equation, what you can say that the response of this system for different sets of input can be studied for just for analyzing the system or with a view towards understanding the nature of the system. So this mathematical model, if you have GS, you can use this mathematical model to study the response of the system for various forms of input with a view towards understanding the nature of the system. Okay, so that's a very good advantage, a very important application of this transfer function. Next, the transfer function of a continuous time system. Since we are dealing with as a continuous time system, that is system excited by continuous time signal. So the transfer function of a continuous time system is expressed as a function of S, and it is only a function of S, and it is not a function of any other real variable. So it is only a function of S and S only, and it will not be a function of any other real variable, even time, or any variable that you consider as an independent variable. No, it will only be a function of S, which is a complex function, complex quantity. So it will be only a function of S. Okay, so it will not be a function of any other quantity. So this is the basic principle of transfer function. Next, the transfer function will include units. It may include unit, it may not include any unit. If it includes unit, that unit will necessary to relate the output to the input, and that is the sole purpose of the unit. Okay. However, that particular unit will not provide any information on the physical structure of the system. So the unit, it may have some unit, but that is only to relate or to express the relation between the output and input, but that doesn't mean it will provide any information regarding the internal structure of the system, because I already have seen from the concept of analogous system, the different types of system, electrical, mechanical, may have same differential equation depicting the dynamic behavior. Even though it's a hybrid system having electrical and mechanical part, even though they have same unit, the internal structure may be different. Although they have some analogous characteristics to a common system. So the unit of a transfer function will only depict the relation between input and output, and it will not provide any information on the internal structure of the system. Just cannot comment anything on whether it's a electrical system or mechanical system. Okay. And finally, in some situations, if the transfer function is unknown, if the transfer function is unknown, then what we can do, we can determine the transfer function experimentally by carrying out some frequency response test. That will be covered in your electrical, control system lab in the next year. So where you will see that given in black box, how we can determine the transfer function or establish the transfer function experimentally. So not necessarily you need a differential equation to obtain the transfer function. The transfer function can also be established experimentally. Okay. So once you establish the transfer function, then you can carry out the same design, okay, or analysis. The final point that I want to depict, or I want to conclude with, is that this transfer function between pair of input can also be defined as Laplace transform of impulse response. So how we all know that the if you consider an unit impulse, that is also called Dirac delta function, then the Laplace transform, or it is called delta t, the Laplace transform of delta t is basically equal to 1. Okay, so impulse response of the system, what will be the impulse response of the system then? Then we define Gs being the transfer function of the system. If it is excited by that direct delta function, we'll get Gs is defined as Laplace of yt divided by Laplace of delta t. Since this Laplace of delta t is nothing but 1, so what you get? You'll get Laplace of gt. Or in other sense, I think this will complicate the matter. What we'll do, instead of this, what I'll write is ys is equal to gs into Laplace of delta t. So that is ys is equal to gs. So what is this ys? Ys is basically the impulse response. So gs is nothing but Laplace transform of the impulse response. Or that's why we normally write where gt is sometimes called the impulse function or impulse transfer function. Is gt. The Laplace of which will get gs. So gs is defined as the Laplace transform of the impulse response, and it can again be represented as GS as a Laplace of GT, right? So this is the basic principle of a transfer function. Now, one thing I think I have missed out regarding this n greater than equal to m. So given this transfer function, there will be three situations. What are the situations? First of all, n greater than m. That is number of numerator pole, numerator order is greater than, always greater than the, sorry, denominator order is greater than the numerator order. So this system is called a strictly proper system, where n is greater than m. Similarly, if n equal to m, then we called it a biproper system. Okay, but in case you have n less than m, then we call it improper system. I think we have seen this situation. So n is greater than m, fine. N equal to m, that is also fine. But for improper systems, as we have seen in inverse Laplace transform, we obtain some additional functions. That is direct delta function or derivative of direct delta function, things like that. Okay. So whenever we're talking about transfer function, we will be talking about rational transfer functions. So we will be mainly concentrating on n greater than m or n equal to m situations. That is for strictly proper or biproper situations, right? Improper transfer functions, they normally do not appear in situations or in normal practice. So the next thing that we should discuss is the procedure for deriving transfer function. Okay, how to derive transfer function given a system. Now, we shall start with the transfer function, deriving transfer function for electrical systems, right? So for that, we need a few assumptions. What are these assumptions? First of all, it is assumed that there is no loading, there is no power is drawn at the output of the system. The first assumption will be no loading. That is, no power should be drawn from the output of the system for which you are trying to derive the transfer function. I'll explain these situations one by one. Okay. Second, if the system consists of more than one non-loading elements or parts in tandem, then the overall transfer function will be the transfer function of individual element and part multiplied. If these elemental parts are non-loading, they are not loading each other. But if the elements load each other, then this concept, that is, I should write the concept here, GS overall transfer function as G1s, G2s, this concept will not hold because of the loading effect between the components. So what you have to do, for if you have this loading effect between the elements, then you have to consider the entire system as a composite system and obtain the corresponding transfer function as a single transfer function. But if they are non-loading, then you can find out the transfer function of the individual element G1, G2, and then multiply them since they are in tandem, right? So this is very important aspect of the transfer function. If you can find out non-rounding elements, then it's better to find out the transfer function of the corresponding elements so that the computational burden is reduced. Last but not the least, it's very important that the system should be approximated by linear, lumped, constant parameter model. The system must be approximated by a linear, lumped, and constant parameter model by making suitable assumptions. Okay, so this transfer function concept requires that system model to be linear, lumped parameter with constant coefficients. So for that, you need to make some suitable assumptions. Let us consider an example. Carry out the. So what we'll have is a series RLC circuit, suppose. So this is your EI, this is your E0, C, R, L. So you have to find out E0S by EIS. That is a transfer function. So what we will do? We shall consider first this in Laplace domain and a current will be flowing like this. So first let us write down the mathematical model. What is the mathematical model? If you apply KVL over here, so L dt plus Ri plus 1 by C integration I dt is equal to EI. And what is the E0? 1 by C integration I dt is equal to E0. Okay, Laplace transform. So this will give you SL IS plus RIS plus 1 by C 1 by S IS is equal to EIS with zero initial conditions. Obviously, that is the primary thing. IC means initial condition. We assume zero initial condition. So from this, again, you will take the Laplace transform and you will get 1 by C 1 by S IS is equal to E0S. Take ratio of these two. So what we will ultimately get is E0S by EIS to be equal to 1 by C 1 by S divided by IS is common. Okay, so it will be like SL plus R plus 1 by C. 1 by. Some of you may leave the transfer function over here, but this is not the correct way of representing it. So what you have to do, you have to take multiply both sides by LC. So what you will get LC S square plus RCS plus 1. You may leave here, but still this is not the final expression for the transfer function. So what you have to do, the final expression for transfer function will be divide both of them by LC. So what you'll get 1 by LC divided by S square plus RC by LC. So this will be the final form of the transfer function. Concept is that whenever writing the denominator equation should be monic. That is, the coefficient of the highest order of the S should be made 1 by suitable adjustment. So this is the final form of the transfer function, and this denominator is a characteristic polynomial. This is called the characteristic polynomial, and the C, if you put this equal to 0, then what you'll get? You'll get the characteristic equation, and that will determine the poles of the system. The roots of these characteristic equations are nothing but the poles of the system, and that determines the nature of the response of the system, and also determines whether the system is stable or unstable. Now, next I'll give you another method of determining the transfer function, because in case you have this method, okay, let me first give an example. So this is a very basic system. Now, if I give you a simple RC circuit, suppose, sorry, so this is your R, this is your C. So say this is your EI, and you have this E0 dash. So what will be the transfer function for this? Quickly calculate this and tell me. Say this is R1 and this is C1. So what will be the transfer function?
Sir, 1 by
Sir, 1 by
CR.
RC by S plus 1 by RC.
Yes, sir.
Right. Now for the time being, I'll write like this for the time being, because there's a certain reason behind it, right? So what I'll do, I'll cascade this. I'll connect another RC part with this. Say R2, C2. So if we had this R2, C2 only, sorry, this will be R1, C1. If you have this R2, C2 part only, then the corresponding output, the transfer function should have been 1 by R2, C2s plus 1. That should be the transfer function. So the overall transfer function, as you expect, I should write this, would be 1 by ideally, and that will give you E0s by EIS to be 1 by R1 C1s plus 1, R2 C2s plus 1. This looks very trivial, but very sorry to say, this is not the case. In fact, this transfer function doesn't hold. Why? Because while determining the transfer function of this first part, when we determine this transfer function, only this portion was there. Right? So this output E0 dash was not loaded. So the output impedance was infinity, and no current was drawn from E0 dash, because the second element, the red part, was not there. The red part of the circuit was not there. So this transfer function was valid. Now, as soon as you connect this, which individually has a transfer function like this portion, if it is calculated individually, it will have a transfer function like this. But as soon as you connect these two, this transfer function will not be valid, because it will draw some current. This second part will draw some current. So there will be loading effect on this first part. And as soon as there is a loading effect in the first part, the assumption of no loading is no longer valid. Consequently, the original transfer function, this will no longer be valid. Right? Although this may be valid because there is no loading on E0 part. But still, this is not valid. This expression 2 will not be valid. Then what you have to do? You have to calculate the transfer function considering individual, not individual circuits, but considering the circuit as a whole. So how that can be done? And consider current I1 over here and a current I2 over here, and you write down the corresponding KVL and mesh equations. So let me just brush up this extra. So what will be the equations for I1? What will be the equation? It will be like 1 by C1 integration I1 minus I2 dt plus R1 I1 is equal to EI. Next, for the second loop, 1 by C1 integration I2 loop, I2 minus I1 dt plus R2 I2 plus 1 by C2 dt equal to 0. And third is 0. Right? So what you have to do? You have to obtain the corresponding Laplace domain representations. So what will be this? So from this we get 1 by C1 into 1 by S I1 minus I2. So whenever writing this I1 and I2 in capital, that means in Laplace domain. So I will be eliminating the burden of writing I1S and I2. No, I should not encourage this. Whenever you are writing in Laplace domain, it's better write the entire expression. And assuming zero initial conditions, obviously, as usual. So R1, I1S. So whenever you're writing in the Laplace domain, you should always use this and bracket and S thing. So you should not miss this. Right? And from this, what you'll get 1 by C2, 1 by S, equals I2S is equal to 0. So from these three equations, what you have to do, you eliminate I1 and I2 and express the ratio E0 by EI. Can you do that? Let's try. Try and eliminate I1 from 1 and 2. Say eliminate I1 from 1 and 2 and express EI and E0 in terms of I2 only. Right? And then you obtain the corresponding transfer function. Okay, I'll give you this. I'll just try at your home. Okay, give you a home task. I'll just write down the transfer function. And the transfer function you have to check. No need to submit, just check for yourself. This will come out to be 1 upon. You write down the see up to this it was okay. Had R1 C2 term not been there, it should have been like a cascade combination of these two parts. But this part, what it indicates is that there's an interaction, okay, between that R1 and C2. So there is obviously a loading effect between the individual component or individual part of the circuit. Right? That's why the total transfer function or the overall transfer function will be modified from what you obtain by cascading these two transfer functions. And this level of modification or the degree to which the overall transfer function will be modified from the cascade transfer function or the product transfer function of individual transfer functions, this degree of modification will depend upon the amount of loading. See, this R1C2 depicts the amount of loading. So, due to this loading effect, the transfer function, overall transfer function will simply not be G1 into G2, but some modified transfer function will get that will include that interaction term R1 into C2. Okay, so this is the basic concept of transfer function. So, whenever you see some loading is present, you should not jump into the conclusion. You have to consider the entire system as a composite one and calculate the transfer function following the basic principle. Right? Now, the only problem that we have been facing here is that to obtain the transfer function, you have to go through the burden of writing the differential equation and then taking it to the Laplace domain and finding out the corresponding transfer function. What if we can solve or we can eliminate this writing down of differential equation part? That is, if you can directly obtain the transfer function, and that can be done via the concept of complex impedance. I think in the circuit theory, you may have gone through this complex impedance part, and because this is nothing but the expression of the individual impedances in S domain. And it becomes convenient to write the Laplace transform equation directly without writing the differential equation. So how? The complex impedance ZS is defined as Vs by Is. What is the Vs? It is the Laplace of voltage across element divided by Laplace of current through the element with zero initial condition. So this is the expression of or relation of or definition of a complex impedance. So given this definition, tell me what will be the complex impedance corresponding to a resistance,
Sir, R.
right? And inductance,
Sir, SL.
how how
Sir,
কি করে পাচ্ছো?
স্যার ডিফারেনশিয়াল ইকুয়েশনে পুট করলেই তো হয়ে যায়।
কিরকম
এল
কোন ডিফারেনশিয়াল ইকুয়েশনটা ইউজ করবে?
স্যার এল ডিআই ডিটি, সেখানে
Right.
ডিআইটাকে ল্যাপ্লাই ট্রান্সফর্ম
B
করলে
equal to now you have to tell me which equation you're using. L d I dt. Okay, fine. Then for capacitance,
1 by SC.
right? Because in this case we have, right? In this way, if you not put down these values of ZS corresponding to different elements R, L, and C in the network, then you can directly write down the transfer function. How? Let us see an example. Suppose we have two complex impedances connected in this manner. Right? This is your EIS. This is yours. Then you can easily write E0s. What will be this ratio? Z2s by Z1s plus Z2s, right? Isn't it? So we can readily obtain the corresponding transfer function just by following this method. So, for example, suppose we have this RC circuit. So, what will be the GS? So, in this case, what is your Z1 R and what is your Z2S? 1 by CS, right? So, what will be the transfer function? Just write Z2 by Z1 plus Z2 will get 1 by RCS plus 1. Similarly, if you have E0, S, yes, L, R, and C. So, what is your Z1S here? R plus SL, and your Z2S is 1 by CS. So, what is your E0S by EIS? Just calculate. So, see, you arrive at the same expression. That is 1 by LC S square plus R by L S plus S. So, see, this is much more trivial and much more easy to obtain the corresponding transfer function just by having the complex impedances in this prescribed form. So, if you can express any network in this complex impedance form, then you can derive the transfer function directly without writing the differential equation, right? Now, since this becomes much easier, now I will try to obtain the transfer function of that cascaded RC circuit. And see, let us see how that can be derived. So, what we have here, the first cascade R1, C1, and the second part R2, C2, right? And this is your E0, and this is your EI. So what you can do, you have to then directly write down the corresponding circuit or draw the corresponding circuit in complex impedance plane. Say this is Z1. For this situation only, I will not write SSS because it's very difficult to write so many S. Z3, Z2, say Z, and since it's in the Laplace domain, A0S, EIS. Now what you can do, you can recast this. In which form? See, Z1 is here. So we have branch Z2 and back. From here, we have Z3 and Z4 to back. And E0 is defined as this. So if you consider this configuration, now let us define the currents. So this is your I. So this I will get diverted in two parts, I1 and I2. So first equation will be I equal to I1 plus I2. Now whenever you have this current division, you should be finding out the corresponding I1 and I2 in terms of I. So with what will be I1? See, I1 will be Z3 plus Z4 divided by Z2 plus Z3 plus Z4 into I. And I don't think I can hold I2 here. Okay, I just write I2 as Z2 I divided by Z2 plus Z3 plus Z. Right? So if you write down this Z1, Z2, what are these values now? What is Z1? R1. What is Z3? R2. What is Z2? 1 by C1s, and Z4 is 1 by C2s. So we've now defined I, and we obtained I1 and I2 in terms of this I. Now let us write down this corresponding voltage balance equation, that is Z2 into I1, this potential between these 2 points, is equal to Z3 plus Z4 into I2, where I1 and I2 is already defined. So this is one equation where you can obtain a ratio between I1 and I2. Again, in KVL, EI is given as Z1I plus Z2I1. So using this two relation, or this simply, you can replace this I1 in terms of I. So what you will get, Z1 plus Z2 again your E0s will be nothing but Z4 I2. So just replace this I2 by I. So that will be Z2 Z4 divided by Z2 plus Z3 plus Z4 I. So see, U0 and EI are now both expressed in terms of I. So if you take the ratio E0 by EI and then replace this Z2, Z1, Z3, Z4, then you'll get the final expression for the transfer function. So finally what you'll get is something like this. So now putting all these values, you get a final form. like this. Here, see, had there not been this term, it would have been simply R1C1S plus 1 multiplied by R2C2S plus 1. So this R1C2 term will be there, and this will indicate that these are loading each other. So there is a loading effect happening between these two elements. So the transfer function will be modified by this particular term R1C2S. So I've just shown you the steps. You should carry out the steps by yourself just to verify whether the values or things that I'm writing, the equations or expressions are right or not. Now, a special case may appear where you have two RC circuits are there still, and that is being isolated by an amplifier of gain K. This amplifier means there's no current is being drawn. This amplifier ensures that no current is drawn from the output of this first part. Okay, so this second part will not load the first part due to this isolation. And in this case, you can simply write where this is your E0S, this is EIS, is equal to K divided by R1C1S plus 1. Okay, so in this way, you can see since there is no loading effect, so they can be considered to be working in cascade form without any loading. So the overall transfer function would be transfer functions of first part multiplied with the amplifier gain multiplied with the transfer function of the second part. So it will be simply this because of no loading effect, right? This is how you can determine the transfer function of systems, electrical systems in general. So this includes the first part of the lecture. Next part we shall discuss about the concept of poles and zeros. I guess you have some in previous class in the circuit theory that depicted the concept of poles and zeros, right? What is the concept of poles and zeros?
Yes, sir.
Okay. I'll just brief you some features. So this zeros will give you some poles of the system. So if you want to define this poles and zeros, I think those are all defined in your circuit theory part. So for that, what we require is I'll just go through very quickly. GS is a function of complex variable S, so that for each value of S in S plane, we'll have a corresponding value of GS. If for each value of S in S plane, you have a unique value of GS, then it's called a GS is called a single valued function of S. Conversely, for each value of GS, if you have a unique value in S plane, then you consider the system to be having a one-to-one mapping between S plane and GS plane, when each point in S plane corresponds to a particular point in GS plane. Similarly, each point in GS plane corresponds to a particular point in S plane. In some situations, from mapping from GS plane to S plane is not valid, because suppose you have this. So for each value of S, we'll have unique value in GS. So S to GS, this is single value. But GS to S is not, because s equal to 0 and s equal to -1 both will correspond to a function gs tends to infinity. So gs tends to infinity will be met in S plane with s equal to 0 and s equal to -1. So this one-to-one correspondence will be lost in this situation. So what we will intend to have gs to be at least single value. That is, for each value of s, there is only a unique value of gs in gs plane, right? So given a single valued function gs, which is a function of a complex variable s, if in a region in s plane gs and all its derivatives exist, that is gs and all its derivative, sorry, derivatives exist in a region, then you call the function gs to be analytic function in that region. See, this function is analytic except for these 2 points. And these 2 points are called the singularities of the function, where the function itself or its derivatives ceases to exist. And the most common form of singularity is nothing but the poles of a system, right? At poles, the system gain system value tends to become infinite. So it's called a singularity of the system. And there may be different types of poles. How? If a function gs, which is analytic and single valued in a neighborhood of a point, say pi, then it is said to have a pole of order r at s equal to pi if the definition is limit s tends to pi, gs is finite, non-zero. This indicates nothing but the fact that gs should contain this factor in its denominator. Since it's having a degree r, so it's called pole of order r. For r equal to 1, it's called a simple pole, right? Similarly, the concept of 0 is that the numerator should contain a factor like this. So here, limit s into zi, this into gs should be finite and non-zero. Then you'll say that at s equal to zi, it has a 0 of order r. If r equal to 1, then it's a simple 0. Now, I'm intending to say the fact that we are very much conversant with the concept of poles and zeros. Suppose we have a system like this. So what about the zeros? S equal to -2. What about the poles? S equal to 0, -1, -3, -3. So it has a single 0 at s equal to -2 and 4 poles at 0, -1, and a double pole at -3, right? But the concept is that since gs is nothing but a rational function of s, which is expressed as a ratio of two polynomials, namely the zero polynomial and the pole polynomial. Therefore, the total number of poles should be equal to total number of zeros. Now, this may look a bit confusing because clearly you can see there is only 1 0 and 3 poles. Whenever talking about total number, this is include finite poles and zeros plus infinite poles and zeros. That is, these are all finite poles and zeros. And there will be poles and zeros at infinity, depending upon the system. So in this case, we can clearly see since the relative order, that is number of poles minus number of zeros, which is called right there relative order, that is number of poles minus number of zeros. So this for this case is 3. So there will be 3 zeros at infinity for this system. So that the total number of zeros becomes 4 and total number of poles are already 4. So that its rationality of the transfer function is maintained. Now you may argue, so how can you tell that there will be 3 zeros at infinity? Let us see. Let us prove that there will be 3 zeros at infinity. What we have is right. So what we'll do, we'll take limit infinity gs. So for that, what I'll do, I'll take out the s terms. Already there is one s. If you take this s1 out, so 1 plus 1 by s. Take another s out, 1 plus 3 by s. So whole square. So obviously there will be limit. I forgot to take the limit. This will be there. So what you'll have in the right hand side is limit s tends to infinity. This ss will get cancelled out. 10 1 plus 2 by s divided by s cube. Out of this 4 s's, 1 will get cancelled out over here. S cube 1 plus 1 by s 1 plus 3 by s whole square. Now we put the limit. So this will be 0, this will be 0, this will be 0. So what we will have? Limit s tends to infinity 10 by s cube. So whatever this value will be 0. So clearly this s tends to infinity indicates a 0 of the system. See, because this ideally becomes 0 because we have limit s tends to infinity gs equal to 0. But what will be the order of the 0? See, in the denominator we have a term S cube. So order of the 0. So there will be 3 zeros at infinity. And that's how you can have total number of zeros, including finite and infinite, to be equal to total number of poles, including finite and infinite. So that the GS remains to be a rational function. A rational function which is expressed as ratio of two polynomials. বোঝা গেল জিনিসটা? The concept of zero and pole at infinity will come
Yes, sir.
handy in the next semester when you'll be learning the concept of root locus, right? So just keep this thing in mind, right? For any transfer function, total number of pole and zero, including finite and infinite pole and zero, should be equal always. The last thing that I will conclude with the features of these poles and zeros, the concept of stability. Obviously, this concept of stability is solely determined by poles of the system. So a LTI system will be stable if the poles are in the left up plane, open left up plane, or it will be marginally stable if the poles are on the complex conjugate poles are on the geometric axis, or a single pole on the geometric axis at origin. If there are multiple poles in geometric axis or multiple poles at origin, then the system will be unstable. So the entire stability of the system will be determined by the location of the poles. So I think I've already mentioned about the Vibo stability. There is given a bounded input. If the output is also bounded, then the system is said to be Vibo stable. There is another concept. This is asymptotic stability. What is this? In absence of any input, the output tends towards the zero or the equilibrium state of the system, irrespective of the initial conditions. Suppose you give an initial condition and let the system to settle down. So what it will do, if it is a stable system, it will settle down to its equilibrium condition, that is zero state. But if it is an unstable system, it will grow unbounded. For example, complex S plane, you have a pole over here. So this is a time response t, this is yt. Suppose I have given it an initial condition of 1, yt is initially 1, and then this is no input is there. So if it is allowed to move, the system will ultimately settle down corresponding to this pole. But if you have pole in the right up plane, what will happen? This will never settle down. It will continue to grow. Because if you find out the expression, one will be e to the minus t something, another will be e to the power plus t. So it will be exponentially growing. So this is asymptotically unstable system, this blue one. And this red one is asymptotically stable system. Right? So in this way, you can also depict the stability of a system by looking at the location of the poles of the system. Then what about zeros? What does this zeros do? Do they play an important role? Yes. I guess you know the respective plots corresponding to different location of the pole in the S plane. Suppose if you place the poles like this on the geometric axis, what is the response? It's normalized scale 1, 2, right? The marginally stable system will be there. And so this is j omega and minus j omega. So what will happen if I put another pair over here? The same location? What will happen? The output will be going like this. Okay, so actually it's a stable system is minus 0. This will become an unstable system. I think these things are already taught in your signal system, circuit theory class. The location of pole and corresponding responses. পড়ানো হয়েছে না পড়ানো হয়নি? জানো কি তোমরা? সবাই চুপ করে গেল। আচ্ছা তো বটেই। স্বর্ণদীপ, ওগুলো কি কভার হয়েছিল
হ্যাঁ
কি?
স্যার।
হয়েছিল?
না স্যার, এগুলো অত ডিটেলসে হয়নি সার্কিট থিওরি ক্লাসে।
আচ্ছা, ডিটেলসে তো হওয়ার কথা না, কারণ তোমাদের তো বেসিক ক্লাস পাওয়া যায়নি।
না স্যার, মানে হয়নি।
ওকে, তাহলে তো একটু মুশকিল। ঠিক আছে, আমি দেখছি একটুখানি ছোট করে হলো কভার করে দেওয়ার চেষ্টা করছি। জাস্ট কয়েকটা ইম্পর্টেন্ট কেসই করাবো, সবকিছু কেস তো করানো যাবে না। ঠিক আছে। আচ্ছা, যদি পোলটা এরকম লেফট হাফে থাকে, তুমি এটা ইনিশিয়াল কন্ডিশন দিয়ে ছেড়ে দাও, এটা লেস ডাউন। But if the pole is in the right half, leave its initial condition, it will grow exponentially, right? So this is one case. If you have complex conjugate poles like this, then what you will have, I think the mistake over here. So this line should be drawn. If you have complex conjugate poles like this, then you have an envelope like this, and in between it will have a damped sinusoid. But if these complex conjugate poles are in the right half plane, the envelope will be like this, and what you'll have is an unstable system. The red ones are the unstable ones, right? Similarly, if you have a single pole at origin, the output response will be like this. It will continue to hold on to the initial condition. But if you have another pole at origin, then it will grow. So the red ones are the unstable systems, and the black ones are the stable systems. And I've already shown you what happens if the poles are on the geometry axis. So clearly, we can conclude that this portion, if the poles are in this portion, they are stable. There's open left up plane, and on this geometry axis, it is only stable until there is a single pole. If there is a multiplicity at geometry axis of pole, then that system will be unstable. Otherwise, it will be a marginally stable system. Okay, so these poles therefore depict the stability of the system. Now, what about zeros then? What does this zeros do? So, what does this zero do is to contribute to the response along with the pole. There will be some other features of the zeros, I think, that will beyond the purview of this class. But what I'll do, I'll just simply give you the basic concept behind the response of a system and the effect of poles and zeros to the response. Suppose we have a system GS given by 1 by S plus 5, which is excited by a step response 1 by S. So what will be your YS? If you take partial fraction, what you'll get? So your YS can be written as 1 by 5 divided by S minus 1 by 5 divided by s plus 5, right? Or what I'll do, I'll put this as plus and this minus. Now, if I now draw the corresponding, so this is nothing but your S plane, real part, imaginary part. So what are there is a pole at origin. This is called the input pole, and we have a pole here that is at -5. That's called the system pole. So the response of a system will have two parts. Okay, one part is the forced response that corresponds to the system pole or the input. Sorry, that corresponds to the input pole. So this part is the forced response, and this forced response will have a given nature that will be determined by the pole of the input pole or the nature of the input, and this is called 1/5. This is called a residue, and this residue in this case is determined by the location of this system pole. So the system pole will contribute to the residue or the gain of this forced response. And the other part of the response, which is called the natural response, I think I have stay free. Just a second, just to make sure that this is corresponding to 1/s. So this is your forced response corresponding to this pole, and this is your natural response corresponding to this blue pole. So overall, this system poles, if there are multiple poles, then you will have multiple this natural response components, and this system pole at -5 will determine both these residues or the intensity of this natural and forced responses. Right now, let us see what will happen if you consider modify this GS to have a 0 at say -2, because in the previous case these residues were solely contributed by the pole. So for GS equal to S plus 2 by S plus 5, if you write down the corresponding YS, what will be it? It will be basically 2 by 5 into S plus 3 by 5 S plus 5. So again, this is a forced response, and this is obviously blue is a natural response. So what has changed? See, the nature of the response is not changed. It is still S and S plus 5. What has changed is this residues or the amplitude of this contributory responses. Because in this case, this residue is not only affected by the system pole, but these zeros also are affecting this residue. So the purpose of this zero or the addition of the zero will cause the relative residues, relative intensity of this forced response and natural response to alter. What it will do? It will alter the residues of this responses, residues of this functions, so that the overall response will be altered because of the presence of the zeros. Right? So this is the effect of zero on the system response as a whole. And there's always another feature that a particular zero is intended to block a particular input signal. Right? so that that input signal is never passed, because we know at zeros the system, overall system becomes zero. So that is beyond the purview of this lecture, but I just wanted to include the fact that zero, although they are called zeros, they have some function to play, and they determine the nature of the response by altering the amplitude of this component of the responses. There is they modify both the amplitude of the forced and the natural responses of the system, right? So since we have started discussing about the time response, in the next class we shall discuss about the time response of a system, right? So today I'll conclude here. So any questions?
স্যার ক্যারেক্টারিস্টিক্স ইকুয়েশনে কি এস এর কোনো নেগেটিভ পাওয়ার থাকতে পারে?
না।
ওকে স্যার।
তুমি যদি এমন ভাবে লিখলে হতে পারে, দেখো তুমি হয়তো ক্যারেক্টারিস্টিক্স ইকুয়েশন এমন ভাবে লিখলে সেটা হতে পারে, তুমি প্রেজেন্ট করতে পারো, কিন্তু যদি রেশনাল ফর্মে লেখো তাহলে কিন্তু কখনোই নেগেটিভ পাওয়া থাকবে না।
আচ্ছা, মানে স্যার আমি এটা জানতে চাইছিলাম, মনে করুন নিউমারেটরে একটা এস এর কিছু একটা পাওয়ার আছে, আমি সেটাকে ডিনোমিনেটরে নিয়ে চলে এলাম ইনভার্স করে, তো সেই রকম কেসে তো
হ্যাঁ
চেঞ্জ
হ্যাঁ,
হয়
সেটা হতে
অনেকটা।
পারে। আমি সেটাই দেখার জন্য তোমাকে বোঝানোর জন্য বলছি। ধরো তুমি এখানে এস টু দি পাওয়ার -3 দিয়ে উপর নিচে গুণ করে দিচ্ছ, -4 দিয়ে।
ইয়েস স্যার। এবার স্যার সেই কেসে তো অনেক সময় রেসপন্সটা চেঞ্জ হয়ে যেতে পারে।
না, হবে না, হবে না, সেটাই বলার। তোমার ধরো এইটা আছে, তোমার কি অর্ডার দিল, এইটা হচ্ছে আমার ট্রান্সফার ফাংশন। তোমাকে সমস্যা কি করতে হবে বলতো, দেন ইউ হ্যাভ টু কনভার্ট দ্যাট টু দিস ফর্ম, এটা পলিনোমিয়াল ফর্ম। এটা কিন্তু পলিনোমিয়াল ফর্মে নেই, এটা কি ফর্মে আছে বলতো? এটা আছে বেসিক্যালি 1/s স্কয়ার 1/s 1/s স্কয়ার 3/s, আচ্ছা এটা হিসেবে -4 হবে একটা, প্লাস 1/s টু দি পাওয়ার 4। এটা কি পলিনোমিয়াল ফর্মে আছে? নেই। You have to convert it to polynomial form. How that can be converted? Multiply numerator and denominator by s to the power 4. So we'll revert back to minus. বুঝলে? যদি এই ফর্মে থাকে, you have to convert it to rational form in this polynomial form.
ওকে স্যার।
You'll find it will be a polynomial of a given order. এটা হতে পারে that you may have asked whether this power can be fraction. That can be there. That's called a, sorry, fractional order system. And there's a branch in our control system and the systems theory that deals with such fractional order systems. Okay. And obviously that is beyond the purview of this lecture, but it can at most be fraction, but it can never be negative. You can represent it as already represented in terms of a negative powers of s, right? But you have to then convert it to a rational polynomial, a ratio of two polynomials in s. So then you'll obviously get a polynomial in s with positive integer as a power, right?
ইয়েস স্যার। ইয়েস স্যার।
Okay. Any other question? Okay then. I guess it's